Hello everyone. Uh, Today I'm gonna to show you the maximum pressure of a step bearing on the software what we call Marc Mentat, which is Adam software. How to compute the maximum pressures of a step bearing having the following parametry: fluid film thickness at entrance is 20 micrometer at entrance. At entrance the pressure is equals to 0. This is entrance section and this is exit section. HE becomes 20 micrometer and the fluid film thickness at exit 10 micrometer. And the length of the bearing is 100 millimeter and the width of the bearing is 100 millimeter and the length of the entrance zone is 50 millimeter. From here to here, entrance zone, the length of entrance zone, Li, which is 50 millimeter, and the exit, the length of exit zone also equals to the length of entrance zone, so it is 50 also. And the other thing is the speed of moving wall. Use equal to the speed of moving wall is 2 meters per second. Fluid dynamic viscosity. The fluid, maybe the fluid is become maybe engine oil and other oil or petroleum oil. So the fluid dynamic viscosity is 0.02 Pascal second. And the relative pressure at the boundaries of the bearing is 0 Pascal. At the entrance, the exit, and at the boundary, all the boundary section, it is 0 Pascal. Oil density, the oil density is 850, maybe it is engine oil, petroleum oil. So using these parameters, we can simulate or we can get the maximum pressure of step bearing using Marc Mentat. Let's start using the Marc Mentat software. And the first thing is we can convert this thing. We have a lot of things on Marc Mentat, structural, thermal, and so on, so on. We can choose hydrodynamic. And here 3D axial, symmetric, and planar. We can choose planar. And the S, we can do our uh, uh, geometry using the SI unit. So it is on the default is on SI unit, so we can choose SI unit. We can convert that that the unit which is given on the micrometer, millimeter, we can convert into meter or SI unit. Let's go. And this is okay. And we can generate the point. Here, point is on, so it's good. And the other thing is we can develop geometry and the mesh at the point. We can add the point. The step bearing is looks like this one. We can choose this coordinate is 0, 0, 0, 0, 0. So 0, inter 0, 0. Here we have 1 point, origin 0, 0, 0. And the length of the bearing, step bearing, is 100 millimeters. So we can convert into meter, it becomes 0.1. And x direction 0.1, enter, 0, enter, 0, enter. And the second point, we can fill it, fill view. So the second point is this one. And the third point, the width of the bearing is this one. You can imagine this one is origins of x, y, z coordinate. So x from here to here 100 millimeter, and the other point y, z is 0, 0. So the next point is in this direction, which we have x and y component, which is length and width, so 100, 100. So we can put x 0.1 enter, y 0.1 enter, z 0. Plane, because we choose plane, not 3D, plane geometry, hydraulic. So 0. And the third point is, yeah, we created the third point. Here it is. And the fourth point is on y-axis. So on y-axis, x is 0, y we have 0 enter, x y 0.1 enter, z 0 enter. Here we have the point. And the next step is let's generate the surfaces. Add surface. Here the command say enter point coordinates at the surface. We generated 4 points. So this one with this one and this one. Surface is created. Surface 1 added this size. And the other thing is let's convert mesh this one, or convert 20 by 20. Yeah, 20 mesh 20. Let's divide the surface 20 by 20. So convert, let's select this one, left click and end, right click outside the surface. So this one is, we can divide the surface into 20 by 20 elements, which is 400 element. We developed the 400 element. So say okay, we are created the surface and we divided the surface into elements. So the other thing is let's add the material property as we have see on the paper. So material property, we can go to new standard mass density or density. We have density 850, and the viscosity, we have seen the viscosity, which is 0.02, like that. Yeah, it's 0.02 Pascal second here, Pascal second. So what we say, add elements. We have 20 by 20 element, that means 400 elements, add. So what we say, add all existing, and we can here calculate the element 400, and end. Okay, enter add material element list as end. So the next step is let's go to boundary condition. Boundary, new hydrodynamics, fixed pressure. The pressure, let's name this one pressure. Let's add pressure. Pressure is 0, as we have on the here. The relative pressure at the borders of the bearing is 0 Pascal. So we can put 0 here, and we can add nodes. Node we choose all, only the border. Okay, add the node. Yeah, then we can click right click. Here we added on 80 nodes. These points are nodes. The rectangular shapes are elements. So we end of lists. We say okay. The next step is we can define the thickness. We can define, we must define thickness. Here the thickness of fluid film, here at the first section, fluid film thickness at entrance is 20 micrometer. From here to here 20, here to different, it is not straight ወጥ የሆነ አይደለም። ስለዚህ ከኢንትራንስ ሴክሽን ኢንትራንስ ሌንግዝ ድረስ ያለው 20 ማይክሮሜትር ነው። and exit section አካባቢ 10 ማይክሮሜትር ነው። bearing, step bearing. We know this thing on machine elements. So we can put these dimensions. Thickness at entrance. At entrance. Thickness at entrance, how much? 20 micrometer. That means 20 e to the power minus 6. You can put in meter. So add nodes. Note we select all. It is from entrance section to the meter point, 50-50. The total length is 100 millimeter, but the entrance section is from entrance to middle section, it is 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can choose 10. From here to here, 1, 2, 3. So this is the middle section. We can choose from here. Here. No. Say back. It's not correct. Add a node. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Until this point. Yeah, now it's correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one is what we call thickness at boundary section. Okay, in this yellow and okay. አሁንም ቲክነስ እንጨምራለን ፊት ለፊተኛው ማለት ነው። at exit 10 e to the power root minus 6 at node and then the next thing is we can add the relative surface velocity, which is relative surface velocity. Let's name it. Name relative surface velocity along x direction, which is 2. Here we have relative surface velocity and u speed of the moving wall 2. So we can add the node all the body is moving, so all existing and okay. And the other thing is we are go to load case steady state, and let's name this thing step bearing SB. Okay, loads, what loads are existing? thickness relative velocity. Okay, then the other thing is we named the load case and the jobs. Let's go to job hydrodynamics. Let's available activity. Here we can select this one, selected what we want, hydrodynamic steady. Initial loads are here. Fix the bear pressure here on this border. Thickness, we assign the thickness in transection, thickness exit section, relative velocity, everything is there. So okay, then we can go to Java results. What we want to simulate the pressure in the pressure integration points. Okay, Java result here we assigned, and the Java parameter default style version, default multi-physics, not multi-physics, old. We can choose old here and okay. Material data file and the check. Let's check, is there error or not, ready for simulation or not. Yeah, when we check it, it says here element type certain has been set for 40 elements, found 0 error and 0 warning, job check complete. Yes, so let's go to run and let's submit for the simulation is submitted. Okay, exit number, let's check what it says. Exit message, this is a successful completion to a Mac simulation, indicating that no additional incremental data was found and that the analysis is complete. So okay, open binary post file. Let's go to simulate model plot result. Deform the shape. Let's see the deform the shape style. Here we can choose contour bands. Here this is the result, contour band. This is bearing pressure. Bearing pressure, job 1, bearing pressure. And what it says, the maximum pressure is 9.573 megapascal, the maximum pressure. So we can write on this section, it's the question asks us, compute the maximal pressures of a steel bearing having the following. So the maximum pressure is here 9.57 megapascal. All right. And so it looks like this. And let's go to flow section. Path plot. How we can plot the path? Node. Let's select node. Let's select the middle section. Here. This red color indicates we have maximum pressure here at the thickness variation. So we can select, let's choose 3 nodes, and we can click here, right click, then add curves where we want to see bearing pressure versus arc length. Yeah, I think there is something bad plot. Okay, what we say here, let's see, add curve arc length here, enter x-axis value arc length, and the y-axis bearing pressure. And bearing pressure, okay. Here we have. So this means the maximum bearing pressure is 9.516 megapascal. That's the answer. So okay, let's back to the simulation section. Here at this point means let me show you here, at this area the pressure is maximum when the change from entrance section to exit section, the pressure is maximum 9.57 megapascal. That's it. So have a nice time. See you again. Bye bye. Bye.